So now we're going to talk about alpha and confidence levels. There's another probability called alpha, or the level of significance that you'll hear about in statistics. Alpha is related to the confidence level. Alpha is the probability that the interval does not contain the unknown population parameter. Mathematically, the alpha plus the confidence level equals 1. If your confidence level is 90%, then the alpha is 10% or 0.10. If your confidence level is 95%, then your alpha is 5% or 0.05. Two-tailed. So if you go back and remember what we did in normal distribution, you oftentimes have the scenario of two tails. A confidence interval for the population mean with a known standard deviation is based on the fact that the sample mean follows an approximately normal distribution. So suppose our sample has a sample mean of 10 and we construct a 90% confidence interval of 5, 15 where the EBM equals 5. To get a 90% confidence interval, we must include the central 90% of the probability of the normal distribution. If we include the central 90%, we leave out a total of alpha of 10% in both tails or 5% in each tails of the normal distribution. So let's look at this picture. So if I look, remember that my sample mean or my point estimate was 10, my EBM was 5, my sample mean minus my EBM is 5, and my sample mean plus my EBM is 15. So the area in purple represents my 90% confidence level for this interval. If you see the area in white, these are my tails. 5% is from 5 below, and 15 and above is another 5%. So using the normal distribution, in summary, as a result of the central limit theorem, the x bar is normally distributed, that is, the uppercase x bar approximates the normal distribution when you have the population mean, comma, the population standard deviation over the square root of the sample size. So let me say that again. Capital X bar approximates the normal distribution when you have the population mean, comma, over the population standard deviation divided by the square root of the sample size. When a population standard deviation is known, we can use the normal distribution to calculate the error bound. So that makes it more robust and easier to use because we know that population standard deviation. So here's some examples of confidence levels and z-scores. If you go back and think about chapter 6, you might remember the z-scores that we used. So again, the error bound of a population mean, the error bound formula for an unknown population mean when the population standard deviation is known is EBM equals the z-score divided by 2, which we already gave it to you in the table before, over the population standard deviation over the square root of the sample size. Again, the z alpha divided by 2 comes from the table. And if you want to be 95% confident, you'd use the 1.96. If you wanted to be 90% confident, you'd use the 1.645. So writing the interpretations. The interpretation should clearly state the confidence level, explain what population parameter is being estimated. Here we're looking at the population mean, and state the confidence interval, both endpoints. So we'd say we estimate with blank % confidence that the true population mean, include the context of the problem, is between blank and blank, include appropriate units.